Acids are recognized by a sour taste, but their defining feature happens underwater. When dissolved, they break apart to release positively charged hydrogen ions. Bases are bitter, soapy compounds that do the exact reverse, dissolving to flood water with negatively charged hydroxyl ions. To the naked eye, a glass of strong acid and a glass of strong base both look exactly like clear drinking water. Relying on taste or touch to tell them apart is a guaranteed way to suffer severe chemical burns. To safely harness these powerful chemical extremes, we must first find a way to interrogate them, forcing them to reveal their hidden ionic identities. To identify these extremes safely, we use chemical indicators, substances that physically change color when exposed to specific ions. This visual shows the pH scale, our map for these chemical identities. A neutral substance sits right in the middle at exactly 7. The closer you move to 0, the higher the concentration of hydrogen ions, making it highly acidic. As you move up toward 14, the hydroxyl ions take over, creating a highly basic environment. Chemists track these shifts using indicators like litmus and phenolphthalein. You can remember how they react with a simple mnemonic. Labor try popcorn with Mayer. Litmus turns blue in a base and red in an acid, while phenolphthalein shifts from pink to completely colorless. For situations where color isn't an option, we use olfactory indicators like onion or vanilla extract. When mixed with a base, these substances completely lose their distinctive smell, but drop them in an acid, and the scent remains entirely unchanged. With reliable tools to identify and measure these invisible ions without physical contact, we can safely observe how they behave under extreme stress. Mixing concentrated acid directly into a pool of water is incredibly dangerous. The interaction is violently exothermic, instantly generating enough heat to boil the water and blast corrosive liquid out of the container. Chemists rely on a strict rule: always add acid to water, drop by drop, while continuously stirring the mixture. When we introduce a highly reactive metal, like zinc, into an acidic environment, the acid aggressively attacks the metal. This reaction forms a solid salt and forces the hydrogen ions to bond together, violently ejecting hydrogen gas in the process. We prove this gas is hydrogen using the POP test. Exposing the trapped gas to an open flame triggers immediate combustion. Acids and bases actively dismantle the chemical bonds of the materials around them. They tear apart stable structures to release raw, trapped elemental energy. We see this exact destructive capacity when acids meet metal carbonates. Pour hydrochloric acid over sodium carbonate, and the reaction rapidly expels carbon dioxide gas, leaving behind a simple salt and water. To verify the invisible gas is actually carbon dioxide, we bubble it through clear lime water. The gas reacts with the calcium inside, instantly creating a milky white precipitate called calcium carbonate. But what happens when you skip the metals and force a concentrated hydrogen-rich acid into a direct collision with a hydroxyl-rich base? This is neutralization. The aggressive, positively charged hydrogen ions smash into the negatively charged hydroxyl ions. Their opposing charges perfectly cancel out, snapping together to form entirely harmless neutral water molecules, while the leftover components drop out as solid crystalline salt. This chemical cancellation process creates the stable, harmless compounds that form the foundation of our daily survival. Look at the chlor-alkali process. By pumping an electric current through basic salt water, we separate it into chlorine gas, hydrogen, and sodium hydroxide. These are the mandatory building blocks for our global water treatment and sanitation industries. Even the food in your kitchen relies on these controlled reactions. Plain baking soda is useful, but by mixing it with a weak, edible acid like tartaric acid, we create baking powder. When heated, that hidden acid forces a sudden release of carbon dioxide. That specific, rapid expansion of carbon dioxide gas pushes outward, forcing dense dough to rise and become soft bread. Some of the salts produced by neutralization have a unique property called water of crystallization. Compounds like washing soda literally trap a precise fixed number of water molecules perfectly inside their crystalline structure, altering their physical properties to help remove permanent hardness from our water supply. Without mastering the exact balance of these neutralized salts, both our modern food production and our industrial sanitation systems would fail. Gypsum is another specialized salt, holding exactly 2 molecules of water in its crystal structure. If we apply precisely 373 Kelvin of heat, it loses exactly 1.5 of those water molecules. This targeted dehydration leaves behind a dry white powder called plaster of Paris. The moment you reintroduce water, it immediately bonds and hardens back into a solid mass. This vital medical tool used to set broken bones is a direct result of understanding how to control these underlying ionic structures. By using simple chemical indicators to map the invisible war between opposing ions, we secure the ability to safely manipulate them. We harness their violent energy to build, protect, and physically heal the world around us.